Hello, everybody. So we start the last lecture in this series. And let me remind you what we talked about during the last lecture. We started consideration of phase space crystals. And what we consider a single particle in the harmonic potential, but this particle is periodically kicked in time with the strength which is given by cosine x function. And then we assume that the kicking is resonant. Harmonic oscillator period is in this unit is 2 pi, and the kicking period corresponds to the period of the harmonic oscillator divided by some integer number s. And then what we do, we switch to the moving frame, and in the moving frame, we average over time. So what we keep only time-independent terms. And in general, this time-independent terms leads to the following effective time-independent Hamiltonian in the moving frame. And if we choose different resonance number, then it turns out that we can observe in the phase space different crystalline structure. So classically, the contour plots of this effective energy reveals, for example, square lattice, where we choose the resonance corresponding to S equal 4. And actually, we are going to analyze precisely this kind of resonance. And then for S equal 4, our effective Hamiltonian can be reduced to a simpler form, which is simply the sum of the cosine x plus cosine p, momentum and position. When we consider the quantum case, quantum particle, then x and p do not commute. The commutation relation for these quantities is equal to I times the effective Planck constant. And this effective Planck constant depends on the units we are working in. And I told you last time, which is very important, will be very important, that this effective Planck constants can be controlled in the experiment. So that is what we had last time. And now let us analyze precisely the square lattice case described by this Hamiltonian. So of course, when we look at this Hamiltonian, we see that this Hamiltonian is periodic in space, which means that when we take the translation operator, which translates over the period of this lattice, translates over the by 2 pi, then this operator commutes with the Hamiltonian, but also we see the periodicity in the momentum direction. So that means that the operator that translates the system over 2 pi, but along the momentum direction, also commutes with the Hamiltonian. But now there is a problem because the commutation of these two operators is not equal 0. This commutator is equal to the following quantity. Times something minus . So looking at this number, at this coefficient, we see that actually it is possible to make this coefficient equal 0 when we choose when this variable, this quantity is equal to integer number. More generally, when we choose the quantity effective Planck constant divided by 2 pi, and if this this quantity is equal to the rational number, then the operator that translates the particle over the along the position direction by 2 pi, and the operator that translates the particle over the period 2 pi times n, where n is given here. I'm sorry. These operators, of course, they commute with the Hamiltonian because there is a periodicity of this Hamiltonian corresponding to these operators, but also these two operators commute with each other. And that means that we can actually, that the eigenstates of our system are also eigenstates of this translational operator. And for example, the eigenvalues of Tx operator are Kx, where Kx effectively is in the range from 0 to 1. The eigenvalues of the Tp operator are, and that goes in the range from 0 to 1 over n. And that this range of these eigenvalues actually determines the Brillouin zone of our crystalline structure. So we have what we have. We have Kx, which we can call quasi-momentum. And this is due to the periodicity in space. And there is also Kp, which can be called quasi-coordinate. And which is due to the periodicity in the momentum direction. So what we can do, we can now apply the Bloch theorem and look for the eigenvalues of the effective Hamiltonian corresponding to different generally quasi-momentums, which is spent by Kx and Kp. There is a corresponding eigenvalues. This is a band index. And in the case of s equal 4, what we have, this eigenvalue problem can be reduced to the following, at the end, to the following equation, where m is an integer number which you have introduced here. This is m. This is a trace of the product of the following matrices. Capital K correspond to the strength of the kicking. Minus so this is the equation for the eigenvalues of our eigenvalue problem, and actually that allows us to calculate different energy bands in the system. So, and we should, okay, looking at this equation, what is important? The important thing is that this is the proper equation provided that our effective Planck constant divided by 2 pi is equal to the rational number. But for different choice of this rational number, we can have different energy bands. And this is one thing. The other thing is that when we look at this equation, it is easy to find that the range of this quantity can be restricted to the range from 0 to 1, because then everything is this equation is periodic with respect to the range of this quantity. Okay, so let us look how the spectrum of our problem looks like for different choice of effective Planck constant. But remember, I will show you different choices, but in each case, lambda over 2 pi is a rational number. So what we see here, that this is a spectrum versus the effective Planck rational numbers of the values of the effective Planck constant. So what we see that this is a so-called Hofstadter butterfly structure. And for different choice of Planck constant, we have different number of energy bands. And for example, when we choose lambda over 2 pi equal 1 over 2, so that means that we are exactly in the middle of this figure, then we see 2 bands, because that this denominator is equal to, but actually there is no energy band because two bands touch each other. So we are here. When lambda over 2 pi is equal 1 over 3, then we have 3 bands. So we are more or less at this position. There are three bands. But when we switch to the value 2/3, then we are actually here. We again have 3 bands, but each band is doubly degenerate. So that is, and this is the the result for the phase space crystal with the square lattice structure. And in this figure, you can see different numbers, and these different numbers are actually the sums of the so-called Chern numbers. And Chern numbers tells us if the system is topologically trivial or it is not, or it is just topologically trivial. And I would like to introduce, to give you some introduction to the topological characterization of the actually periodic structure, system with periodic structure in space, and actually it can be also applied to this phase space crystals. And I'm not going to introduce very profound mathematical basis. I would rather tell you about Chern number from the physical point of view. And this is, so that is why, okay, so what we have to introduce, and I introduce the part which we often called reminder. And physical point of view always start with the Berry phases. Berry phase, and then I will tell you about Chern number. Actually, the first Chern number. So Berry phase. Berry phase is related to the adiabatic description of the adiabatic evolution of the system. So how it goes? We have the Hamiltonian. Suppose that the Hamiltonian depends on a certain set of parameters. So assume that the manifold of the parameters is two-dimensional. Of course, it can be any dimension, but let's say in our case, we are at the end we are interested in the two-dimensional system. That is why I prefer to stick to this choice. So what we have the Hamiltonian, which depends on on a few parameters, and then the eigenvalue problem, eigenstate of this Hamiltonian, of course, also depends on these parameters. The same is for the eigenvalue. Okay. So now assume that at t equals 0, we prepare the system in a certain eigenstate. So this is the state of the system at time equal 0. But now we start changing the parameters of the system, but very slowly, adiabatically, which means that now our parameters of the system start depending on time. And if we change the parameters of the system very slowly, then we expect that our system, initially prepared in a certain eigenstate, will follow this eigenstate in time. And this is possible if the evolution is sufficiently slow and provided that the eigenvalue, the corresponding eigenvalue of the state at a certain time is never degenerate. So then, okay, and the evolution lasts some time, and it's supposed that at t equal capital T, we return to the initial values of the parameters. So then what we expect that at the end of the evolution, the system is in the same eigenstate. And in the same eigenstate, that means that this is equal to psi of x of 0. So the probability of the occupation of other eigenstates is negligible. But this is not the end of the story, because what can change? The phase of this state can change. And there are actually two contributions to the phase. There is dynamical contribution, and there is something which we will call geometrical contribution. This dynamical contribution is actually quite natural, because if we prepare the system in a certain eigenstate, then what we expect that the time evolution is related to the phase factor, which oscillates with the eigenvalue of the corresponding eigenvalue. But because we are changing the eigenvalue, so this phase corresponds to the integration of the eigenvalue over time. So that's a natural dynamical contribution. But there is a second contribution. A second contribution, of course, that comes from it's a quite simple derivation of the adiabatic adiabatical approximation because we start with the Schrödinger equation and we time-dependent Schrödinger equation, and the only things what we have to introduce that the evolution is sufficiently slow so that the projection of the time derivative of our initial state on the other states is negligible. And then we end up basically in the system which follow the initial eigenstate. Okay, so the geometrical phase corresponds to the following quantity. And this is that one. And the integration over time. So what we can do, we can actually perform the time derivative of the state by first calculating the gradient over the system parameters, and then calculating the derivative of the parameters with respect to time. That's time. But that means that we can get rid of time, because what we have an integration over a certain period, but our system starts from the certain value of the parameters, and at the end it comes to the same. It comes back to the same value. So that can be reduced to the following integration over space, over the curve in the parameter space. And now what we obtain something where there is no time. This quantity can be calculated even if there is no adiabatic evolution. This is purely geometrical quantity. And the quantity inside this integral will denote it by a of x. And this is something which is called Berry connection. Okay. So, of course, we probably know very well that this geometrical phase was known for years, but it was not considered as an important contribution to the system of evolution because people thought that it can be eliminated by the gauge transformation. What it means? It means that suppose when we consider a state of the system for a fixed value of the parameters, we can always change the global phase of this state, and we can define another state which is exactly equivalent to the state before the transformation. So physically, these are the same state because we have introduced just the constant phase. Parameter is constant. And then let us calculate how Berry connections changes when we perform this gauge transformation. What we do, we calculate our Berry connections for this new state. which is according to the definition simply the following quantity. And then when we introduce the expression for our psi prime state, we obtain that this is the Berry connections for the state before the transformation minus gradient of the phase. Okay, that's nice. So it suggests that indeed, by the proper choice of the phase, by the proper gauge transformation, we should eliminate our Berry connections and make this quantity equal 0. However, when we calculate the geometric phase, which is simply the Berry connection integrated over the closed loop. So this is after the gauge transformation, and then it can be expressed as the Berry connection before gauge transformation minus the following integral. But this is the integral over the closed loop of the gradient of the function. So that is equal 0. So that means that the Berry connection changes when we perform gauge transformation, but the geometrical phase is gauge invariant. And also looking at this expression, how our Berry connections transform with respect to the gauge transformation, we see the similarities to the classical electrodynamics, because it transforms in a similar way as the vector potential. And that is why Berry connections is often called Berry vector potential. Okay, so this is one thing, but now, and why, and another similarity to the electrodynamics is that actually this quantity can be expressed as a flux of the magnetic field through the surface, which is with the boundary, whose boundary is this closed curve. And of course, we know that the flux of the magnetic field is something measurable and gauge invariant, and that is why our geometrical phase is also gauge invariant. Okay, so let us introduce the corresponding quantity, which in electrodynamics is a magnetic field. So let us introduce the second rank tensor, which is simply the following quantity. Remember that we are we consider 2-dimensional manifold for the parameters of the system. And this quantity for the Berry phase problem can be expressed as the following quantity. And this is something which is called Berry curvature. And Berry curvature, in contrast to the Berry vector potential, is gauge invariant. And then the geometrical phase can be written, reduced by means of the Stokes theorem to the flux of the Berry curvature to the surface, where the boundary of the surface is our closed curve. Okay, so that is first part. This is just I wanted to remind you the very phase. But now let us consider different system. Let us consider the system two-dimensional problem with periodic potential. So we have a particle which is described by the kinetic energy and the potential which is periodic in space. And we are in 2D. So these are basically the Bravais vectors of our periodic structure in space. So then, of course, we know that Bloch theorem allows us to write the eigenstate of this Hamiltonian in the following form. We have the band index, we have the quasi-momentum, and of course, remember that this quasi-momentum is a two-dimensional vector, and this U function is periodic with the period of our potential, special period of the potential. And then the eigenvalue problem with this Hamiltonian reduces to the eigenvalue problem for the U function, where this is P plus K Now, when we look at this eigenvalue problem, so we can say that our quasi-momentum, which is the well-defined quantity, looks the same as the quantity x, which is a parameter of this eigenvalue equation. So that means that we can identify the space of the system parameters with the quasi-momenta of this periodic system in space. So, and then what we can do, we can define Berry curvature. Let us introduce the index. This is a Berry curvature corresponding to the N energy band. Remember that in this here we have different eigenstates of the system, which are denoted by the index N. And now what we have also eigenstates which correspond to different index N, which corresponds to different band of the system. For each K, we have certain series of the eigenstates. Okay, so the Berry curvature is exactly the same as we introduced in the former previous slide, but only the change is that we have different notation for the system parameter. And of course, once we have Berry curvature, we can calculate the flux, this Berry curvature through the any surface, and we can calculate through the Brillouin zone. And what else? We know that if we take the quasi-momentum K and quasi-momentum where we add a certain Bravais vector in the reciprocal space, these two vectors are equivalent. So that means that the topology of our Brillouin zone is actually a torus topology. Torus is a closed surface, and then we can go to the mathematics of the fiber bundles, and then what we get that the Berry curvature over a closed surface is always quantized. When it is quantized, it corresponds to the integer multiple of 2 pi. So then we take this flux of the Berry curvature through our Brillouin zone, through our torus in the quasi-momentum space. Then, and if we divide this flux by 2 pi, then we obtain integer quantity, and this integer quantity is called the first Chern number. And this integer is a topological invariant. And so what we have? We have, so the first Chern number, this integer quantity is a topological invariant, and it can only change if you have a band structure and we can calculate the Chern number of a certain band. This Chern number can change if the gap is closed. That is one thing. The other thing is that if our system, if we calculate a Chern number for each band for our system, and for each band this Chern number is equal 0, then we have topologically trivial system. Otherwise, if any Chern number is not equal 0, then we have something what we call Chern insulator. Moreover, when we sum all Chern numbers over all energy bands, then it's not difficult to show that the sum is equal to 0. And as I told you that if Chern number is not equal to 0, then we deal with the Chern insulator. And the simplest, one of the most important Chern insulator is the system which reveals quantum Hall effect. So just let me tell you a few words about this. So what we have, suppose that we have a two-dimensional structure, which is infinite along one direction. We have strong magnetic field, and suppose that this is x direction, this is y direction, and this is 2D structure, and what we do, suppose that we apply current along x, certain current, and what we measure the voltage along y. And then we can define and so-called Hall resistance. Which is the ratio of Vy over Ix. And in the Hall system is inversely proportional to the Hall conductivity. And now what is extremely important, that the Hall conductivity is quantized, and one can show that Hall conductivity is equal to is determined by the sum of the first Chern number, and the sum goes over the field bands, field energy band. So we have a certain Fermi level, and all bands below the Fermi level are occupied. And if the Fermi level is in the gap, then if we have had infinite system, then it would be insulating system. And if we don't have, if we have a finite system, if we have edges, then it turns out that on the edges, due to the fact that the system is topologically non-trivial, there are edge states which are responsible for the whole conductivity. And in experiment, what we can do, we can change how many bands are filled by changing the value of this strong magnetic field. So this Chern number is extremely important quantity, and it also tells us that when the system is topologically trivial or not trivial. And coming back to our phase space crystal, so it turns out that this, at first glance, very simple Hamiltonian, because this is okay. The equation is very simple, and this simple system can reveals band structure, and this band structure, depending what value of the effective Planck constants we choose, this band can possess topologically non-trivial properties. So I think that is all concerning phase space crystals. And now we can switch to the last part of the lecture. This last part of the lecture will be related to photonic time crystals. Photonic time crystals correspond to the dielectric medium where the dielectric constant is periodically changing in time. And the first publication which I have found concerning this kind of system is Bianca and co-workers. That was published in Physical Review E in 2007. So this is before the new era of time crystals. There is a nice, very recent review article on photonics in time-varying media. This review is by co-workers, and it is published in Advanced Photonics. A year ago. Okay, so that's this is a good moment to have a break, and after a break, we will continue. So we can come back to the lecture. Before I tell you about photonic time crystals, let me consider propagation of electromagnetic waves in a dielectric medium. Okay, so now let's consider the so-called something which we call special interface. Now it's working. I'm sorry. Special interface. And so what we have, let us consider propagation along in 1D. So basically, we are interested in the propagation of the wave along z direction, and here we have time and z axis. So now suppose that we have at a certain z we have a change of the dielectric constant. And suppose that we have a wave packet which propagates with a certain velocity. So this is an incident wave. And then we know that then there is some part of the wave is transmitted to the part of the medium with different dielectric constant, but also we know that some can be reflected. And of course, when we consider plane wave propagation, then we know the Fresnel equation and all this stuff. But now, okay, one important thing is that what is conserved in this in this wave propagation is the energy. So when we consider the frequency, certain frequency, this frequency or energy is conserved. And now let us consider temporal interface. So we have similar plot, but now at certain t, not the electric constant changes. So we have again the propagation of the wave packet at a certain time. The dielectric constant is changed. So then what we expect that there is also, let's say, propagation, but in general with different velocity. So this is a transmitted part. And now what happens? One would say there is reflection, but no, we cannot go back in time. But there is a reflection because in the solution, what changes, the sign in front of the frequency is changed and the wave is reflected. So but now what we have, what is conserved in this wave propagation is the momentum, because we consider homogeneous, especially homogeneous medium. Nothing happens when we go from one point in space to the other. So that means that the momentum is concerned. Okay, so that is what we expect when there is a spatial or temporal interface. But now what we want to consider, what happens when the dielectric constant is changing periodically. But before I switch to time crystals, well, let us consider something which is much better known and which is in a laboratory is a standard medium to control, investigate, and to prepare, which are photonic crystal, but in space. First part is, I'm sorry. So of course, what we assume that we have there is no free charges in our medium, there is no current, and the medium is linear and not magnetic. So that means that magnetic induction is simply equal to the magnetic field, and this is linear medium. That means that displacement field is proportional to the electric field, and the coefficient which is in front of this electric field is just the electric constant. So then the Maxwell equations look as follows. And what we want, and of course that nothing depends on, let's say, explicitly on time. So we can look for the solution which is harmonic in time. So we assume that the solution for the electric field can be parameterized by some vector which depends only on the spatial coordinate, and it is evolving harmonically in time. And the same for magnetic field. Then, so what we do with this is as a standard situation, we calculate the curl of this equation and then substitute, let's say, the second equation of the fourth equation of Maxwell, of this Maxwell equation. And so what we get okay, double curl. So minus omega square over c square, where c is a vacuum speed of light. Okay, so that's now let us assume that the electric constant changes periodically in space, but only along that direction. So there is a certain spatial periodicity. And also assume that now we are interested in the propagation of the electromagnetic waves along z direction, and the wave is polarized along x direction. So that means that for this special part of the solution, we assume that this is a vector along x, there is a polarization, times there's a certain function which depends only on that. So then, substituting this form of the solution to our equation, we basically obtain the following problem to solve. Okay. And because our dielectric constant is periodic in space, we can look for the solution in the form of the Bloch waves. So we assume that E of z is a certain function which is periodic in space with the period of the changes of the dielectric constant. And there is some exponential function. What we have here, this is a band index, but this is a, you will see that this is a frequency band index. This is an index of the energy bands, basically. And there are a that quantity which we can call quasi wave number, which is let's say the analog of the quasi momentum. Wave vector, but we consider actually one dimension situation. So this is, I call it vector. And of course, due to, as usually in the case of the Bloch theorem, we can define the Brillouin zone, which means that this quasi wave vector we can restrict to the following range of Q. Okay, so now let us consider how, let me show you an example of the solution of this equation. That is, so assume that we have a dielectric medium when you have different layers with different dielectric constant. And in this example, actually we have layer A, where we have dielectric constant equal 4. The width of this layer is 0.4 times the periodicity space. And there is also B layer, and then dielectric constant is simply equal 1. And the width of this layer is 0.6 periodicity. And how to find the, this is the, in this case the solution of the for the Bloch waves is quite easily can be quite easily found because in each layer we have constant dielectric constant, and then that means that in each layer we have simply the plane wave solution, and the only problem is that we have glue different solution together by imposing the continuity condition. So in each layer we can define the wave number which is determined by the dielectric constant, and then the continuity condition leads to the following equation. This Ka is given in the upper equation. And this equation allows us to find eigenvalues for frequency. And it, of course, the frequency is a conserved quantity, but it turns out that not all values of the frequency are allowed in our medium. And here, this is the solutions. It turns out that the frequency, which is here, form frequency bands. That's basically the solution of this equation, which can be reduced in this particular example to the following equation. And now what happens? It happens that when we have a medium, finite medium, and the wave propagates towards this medium, and we choose the frequency, which is in the frequency band, for example, here, then some part of the wave is transmitted, some part of the wave is reflected. But when we choose the frequency in the gap between the band, then there is a total reflection of the wave from this medium. So that is the short description of the photonic crystal in space. And now we are ready to switch to the photonic crystal in time to compare how it is different from this photonic space crystals. That is now. So now we assume that the dielectric constant is changing periodically, but in time. And again, we assume that we have non-magnetic linear medium, and we also assume that the medium can respond instantaneously to the change of the dielectric constant. That means that the displacement field follows the changes of the dielectric constant. And then the Maxwell equations look, in this case, looks as follows. And again, what we do, we apply the curve to this second equation and employ the fourth equation. And then we obtain, it allows us to eliminate the magnetic field, and we obtain the following equation for the electric field. And again, let us consider that the wave is propagating along Z direction and is polarized along X direction. So we are looking for the solution of this equation in the following form. This is a polarization. This is function which depends on time, and because we have homogeneous medium, so the wave vector is a good quantity, is a conserved quantity. So that means that we can look in the solution in the form of the harmonic function in space. So when we substitute this solution to the above equation, then we obtain the following final equation. And now, because we have periodicity in time, so we can look for the solution in the form of Floquet states. Yes, sure. Thank you. Yes, this is derivative over something. Okay, thank you. Okay, so that is so we are looking for the solution in the following form. There is certain function which is periodic in time. The periodicity of the of the changes of the dielectric constant. There is something which usually corresponds to the Floquet system. When we have a Floquet system with particle driven periodically, then we have a quasi-momentum. But we have here quasi-frequency. And now that is the index corresponding to wave number band index. And again, like in a Floquet, usually in the Floquet system, can restrict to the Floquet zone. And now let us consider the following examples. Example where we have where we have periodic changes of the dielectric constant, but it changes just in a similar way as in the former case for the photonic crystalline space. So we have different times intervals, and in different times intervals, the dielectric constant is constant. So that means that, for example, for this period, dielectric constant is equal 3. But in that period, this is all too small. Okay. It is equal 1. Okay, so when we have infinite time crystals, so it starts from the, let's say, from minus infinity to plus infinity, then we can obtain the quasi-frequency eigenvalues, and it turns out that although momentum, the wave vector, is a conserved quantity, not all values of this wave number are allowed. And we observed the formation of the band structure, but along the quasi-momentum direction. And now the question is, what happens when our wave propagates in the presence of this time crystal? So suppose that we consider finite time crystals, finite in time. So initially, we prepare the wave packet, which is propagating along that direction. So that is just to make it more clear. So the certain time we have certain width of the wave packet in space. And this wave packet is propagating in time, changes the position in time. And of course, because we have the dispersion relation for the electromagnetic waves is linear, always propagate with the same velocity. So there is no spreading of this wave packet, and it has the same shape. And it happens up to this moment in time when we turn on the time crystals, when our time crystals begins. And in this plot, we assume that we have chosen the wave number of corresponding to this wave packet in the band, in a certain band of the wave number. So of course, this wave packet is a superposition of many different waves, but we assume that there is some central wave number. There is some spreading, and all of them are located in the certain frequency band. So of course, so what happens when we turn on the time crystal? Then there is some that most part of the wave packet keeps propagating in the same direction, but there is certain reflection. There is some fraction of the wave packet starts propagating in the opposite direction. And it happens until we turn off the time crystal. And when we turn off the time crystal, which happens at this moment of time, then we have at the boundary, our wave packet also splits in two. Most part of the wave packet keeps propagating the same direction, but there is certain reflection. But the same happened with the previously reflected part of the wave packet, because it propagates in the opposite direction. But at the moment when we turn off the time crystal, there is most of this wave packet keep going in the same direction, but there is certain reflection. But now what happens when we choose the wave number in the gap of the in this wave number direction, let's say coordinate? And then it is very interesting, because in the photonic crystal in space, we know that there is a total reflection, because there is a solution which is, when we consider the solution which enters a medium, it is exponentially suppressed when we go inside the medium. So basically everything is reflected. But here, when we are in the gap, and we turn on the time crystal, then we can have also exponential solution with real exponent, and the solution which is exponentially the part of the solution which is exponentially suppressed in time, but also the part of the solution which exponentially diverges in time. And this diverging solution is what you see here. So initially we have, because in this color, this is different color code as compared to this case. We have the same initial wave packet propagating before we turn on the time crystal. So this is exactly what we have here. But when we turn on time crystal, then we have during the presence of these time crystals, we are in the gap. There is a huge amplification of the pulse, and from what it comes from the fact that we are driving the system in time. So our driving is responsible for the amplification of this pulse. So when the when the crystal is over, so we are here, then there is no further amplification, but we observe two pulses with intensities much larger than our initial pulse. So that's what is happening when wave packet actually enter the time crystal system. And a few comments. One comment is that it looks very nice, but it is very difficult experimentally. Yes. Okay. And there's here is not because we have a homogeneous medium. The medium is homogeneous. Whatever direction you choose for the initial propagation of the wave, it doesn't matter. In a Fresnel model, okay, the part of the medium is homogeneous, but an entire system is not homogeneous because at some, let's say, part of the space you change the dielectric constant. It is not homogeneous. That is why the momentum is not conserved. What? I'm sorry? Not entirely, because okay, I would like to repeat the question because there is a question concerns the similarity to the special case and to the description within the Fresnel equation. Here, this is very important. The important differences is related to which quantity is conserved. In the standard situation, we have a time-independent medium, so the energy, the frequency is conserved. Here, everything is happening in time, so the energy is not longer conserved because we have time periodic changes of the system parameters. But because we do changes in the entire space in the same way, the medium is homogeneous and the wave vector is conserved. So simply we cannot map exactly what we have in the Fresnel case to the time periodic medium. Can you repeat this last? Mm-hmm. Yes. I think that you mean of course pointing vector can still be defined, but what are consequences of the pointing vector is related actually to the conservation of the energy in the system. So in this sense, there is no conservation of energy because explicitly we assume that the system is driven in time. So the consequences are different. We can, of course, we can, because this is the where is the output of our life? It comes from the solution of the Maxwell equation, and that, and the I think that we have to get used to this, let's say, changes of the system, because now we usually we are familiar with the changes of the system parameters in space, but now we have to get familiar which quantity, how different quantities behave when we switch to the driven the system in time. So that's, and one, this is also that is related to the remark which I wanted to tell you, that of course the nice reflection of the wave when we have, let's say, special interface, then let's say Fresnel equation, and now let's say quite strong reflection of the wave is thanks to the fact that there is an abrupt changes of the system parameters in space. And of course, here when we switch to the temporal interface, there is a significant reflection when there is also the abrupt changes of the system parameters in time. What it means abrupt? Abrupt means that it is faster, or at least comparable to the period of the electromagnetic waves. So in the optical regime, to change the properties of the medium faster than the frequency of the optical wave is not easy. This is one thing. The other thing is that the changes of the dielectric constants cannot be negligible. They should be of the order of unity in order to see, let's say, nice and big gaps in the wave number domain. And that this is so experimentally it has not been demonstrated in the optical regime. There are some experiments in the microwave regime, but not in the optical one. But now, at the end, I would like to comment that because we have this time crystal. This is just an example of time crystal, photonic time crystal. But now let's assume that we have not one time crystal, but two different time crystals glued together. And then it turns out that with the proper choice of this time crystal structure, this model behaves in a similar way like topological SSH model. And then it turns out that one can observe the edge states which are localized on the border between these two time crystals. So that is, so this field is also extremely interesting, and it is developing currently. And I would like to tell you that concerning the topological time crystals, I'm sorry, topological photonic time crystals, sorry. There is a paper by Lustig and co-workers. This is 2018. But I'm not going to talk about this because this is actually the end of the story, the last lecture. So it was my pleasure to give you the lecture, and I hope that you can find it useful. And that's it. So thank you very much.